Hello once again. I think it's good time to start. Welcome to the seventh and bonus webinar of our Motion HVACR series. And today we have a guest speaker, Mark Mitro. He is the Global Product Manager for Variable Speed AC Motors. And he will introduce his topic just in a moment. And before he does so, I will just mention that the session is being recorded and we will share all the materials afterwards on the webinar web pages. And now, Mark, please to you.
Well, good morning or good afternoon, as the case may be. As Olga indicated, this is a discussion on wired air efficiency and motor technology. It's based on the Center RM, which is an existing technology from ABB, and what we call the second generation iteration of that, where we're adding ferrites to it. So we're going to do a discussion on that technology and why we believe it helps in optimizing wired air efficiency for HVAC system design. We'll talk about some of the industry trends and what precipitated coming up with a second generation design, and then do a comparison of existing motor technologies and where this fits within that existing scope of motor technologies that are out today. We'll do a little brief discussion on IEC design considerations, the lower voltage, a little bit more current draw, so how the ratings match up with our NEMA products. And then we'll show actual lab testing data, and then that data actually applied to various fan curves and discuss partial load efficiency. And then go through some of the fan designs and impact on wired air efficiency and design considerations. So without further ado, this will be about a 30 to 35 minute presentation. It's a brief overview. However, we'll be more than happy to have follow-up discussions and get into more technical details if you are interested. So, why is this important? Well, obviously, the primary reason is that motors consume about 1/3 of the world's electricity, and that's a sizable amount. And so when you're looking at the increase in energy demand by 2040, it's expected to double, which is equivalent to adding the electric market the size of, China. So it's a sizable increase. And so the power companies and the power grid demand have to be minimized where possible. And when you have systems like pump, fan, and compressed air systems that make up the majority of HVAC applications, consuming 40, 20, 22% of the overall demand of that 1/3 of the electricity that's consumed, that's a sizable area to focus on when going after energy savings. So when you look at, well, here in the US, it's the Department of Energy, but it's not the same internationally. But when you look at efficiency standard organizations, that's why they're focused so heavily on this segment. And they're not just focused on the components anymore. They're trying to drive more of that wired air efficiency and the overall system efficiency in the designs, because that's almost more critical. So, in HVAC, efficiency is the top design consideration. We just covered why, and also the pressures from various regulatory agencies that are looking at putting in new standards for total system efficiency. EC fans is a technology that's been out for some time, that it's been gaining favorability because it's high efficiency. It integrates a brushless DC permanent magnet motor, which can have between IE4 and low IE5 level efficiency, and a DC power converter. The control in itself isn't generally efficient, only at its maximum operating point, and which leads to, when you're running at partial load and partial speed, which most HVAC applications run at, the control itself suffers. So when you're looking at system dynamics, it's not just the motor, because the motor is running variable speed, and then you have a drive on it or a power converter, and how efficient is that power converter at partial loads as well. So you have to look at that in addition to the fan or the pump design. And because of that, uh, uh, we developed this new technology, the center RM squared, second generation center RM motor. And it's really designed around providing a broad peak efficiency, what we call island or operating range of efficiency that generates more flexibility and pump or fan for the application. And so we'll discuss that a little bit. So, and we already talked about real efficiency has to be evaluated on the total system and the wire to air efficiency. And quite honestly, the pump or the fan design makes up the primary efficiency losses in the system. So anything we can do to take the motor out of the equation, make it a stable constant that you can depend on to maintain high efficiency across the widest operating range possible is a benefit, because then you can pick the optimal pump or fan for that system and really optimize the overall wired air efficiency. So that's the real, putting that up front, but that's the real takeaway here. So, this kind of motor technology is going to enable you to be able to pick between multiple pump and fan curve systems and come up with the optimal design that's going to give that peak overall system efficiency. So how are we doing that? And how is this a little bit different than a traditional center RM or even a true permanent magnet motor? First off, it's based on a standard induction motor. So it operates on the same principles as an induction motor for rotation. It has a standard induction stator winding. So nothing is different there. And then we add in the synchronous reluctance motor, which is the center RM rotor, which you're familiar with. Center RM motors have flux barriers. That's the air gaps. It's literally just these air gaps here. Air gaps are non-conductive. So by having air gaps, you can channel the current flow in the rotor. And basically what that does is that eliminates the losses in the rotor. So in a standard induction motor, which is about IE3, you have losses in the rotor because it's a solid rotor. And you get circulating currents and losses that produce lower efficiency and heat. So a center RM motor does a great job of eliminating rotor losses, but it's typically characterized by a higher current draw and a lower power factor. So the center RM squared motor enhances that by adding ferrite magnet material to the rotor. Now this is different than traditional permanent magnet motors because those use what we call rare earth magnet material. It's expensive, it's hard to source, it's volatile on the commodity market. So there's a lot of factors that don't make it attractive. Ferrites are ceramic, think like refrigerator magnet material, easy to source, readily available, and those get inserted into the slots that are into the rotor, and you get a ferrite assisted synchronous reluctance rotor here. So what that does is you add in magnet material, and there's no current required because it's constantly magnetized. So that magnetic field actually produces, like, now the stator winding only really has to produce torque on demand above and beyond what the ferrites generate. So that reduces your losses in the stator. So you have a synchronous reluctance rotor with no losses. You've got the ferrites that take up some of the torque demand and reduce stator losses. And so now you increase efficiency even more and you get into the IE5 range. But the other added benefit of that is it drops the current draw. And I'll show some of that on motor current draw. So now you have a current draw on the motor that's typically lower than an induction motor current draw. And in a lot of cases, you can put a smaller power converter on it and save size and cost associated with the power converter because you don't need as much amps out of it. And I always like to think of a drive. It's not delivering horsepower or kW, it's delivering amps. So you size the amp of the converter to the amp draw of the motor, and we're saying we have a lower amp draw. But then we also boost up our power factor into the 92 to 98% range, depending on the kW or the horsepower. And so it's an overall second generation of that center RM design that improves on all of these aspects and gives a very high efficient motor, but it also is characterized by a speed torque profile that at low speed and lower load points, it's going to maintain that efficiency at a much flatter profile than other technologies. So we'll show that with some actual lab data. So this is just a graphical representation of the different efficiency levels and the losses. So we already covered this, but you have rotor losses here in an induction motor that in a synchronous reluctance, the center RM are eliminated. So you have lower losses and higher efficiency. And then here you go into the IE5 and you have more lines of flux. You can see that quite clearly here when you just see these lines of flux, and the more lines of flux you have, more torque you're producing and the more power density. So that's the other aspect of this. You get a very power dense design, can produce good torque out of a smaller frame motor. So in a lot of cases, you look at a 15 kW or a 20 horsepower motor, it's typically in a 280 frame, or I believe that would be an IEC 132 frame, or maybe higher. I need to but we can go down in size. So we can put a 20 horsepower 15 kW in a 210 frame. So, it's a more power dense design because it has basically less losses in it, generates less heat, draws less current. And that produces lower temperatures. So when you look here in this comparison, this is lab testing. We put the exact same drive on the back end of this, so you have equal comparison. And you can see about 84.3 degrees C rise in the induction motor. And in this center RM motor, you've got a squared motor, the second generation, 68.2. So that's about a 16 degrees Celsius lower temperature rise, 20% cooler running motor. Allows us to get the motor into a smaller frame size, but it's actually putting less heat into the airstream. It's the motor runs cooler, so that's less thermal stress on the windings. That's a lot less stress on the bearing grease. For every I think it was 10 degrees C rise in temperature, it cuts the bearing life in half or something because of the grease thermals. So you get a longer running product. It's cooler, less added heat into the airstream as well. This is kind of a comparison of all the technologies out there and where they align. I'm not going to take a whole lot of time on this because this is just a brief overview. But again, you have standard induction motors. They're widely accepted out there. They're used in a lot of application. The benefit is they start across the line. When you get into anything past that, like a center RM motor, center RM squared, electrically commutated motors, and true permanent magnet motors, they all have to have a drive on them. Now, the fact is, most applications in HVAC now are on variable speed. So that's really not a detriment, but just to make you aware of that. So again, we already talked about the center RM motor and the limitations there. Electrically commutated motors that you see there are typically always supplied as a package. So they have the motor, they have the drive built right into it, and then the entire fan assembly. And so I'll highlight this later, but one of the differences is we're really targeting the center RM square, the second generation product, more on standard discrete component replacements. So, the advantage here is from a serviceability standpoint. If something goes out in the system, the motor, the drive, or something goes wrong with the fan, they're all individually serviceable and replaceable. You don't have to replace the entire unit like you have on these integrated units. There's benefits there. They're high efficient. They're easy to use and maintain, and they're well recognized in the market. And they're compact, and they're a good design. But I'm just showing you the differential. We think we have a wider efficiency operating range, plus more serviceable with the discrete components. And then you have real permanent magnet motors. These are great designs, but they're typically not cost effective at lower horsepowers where you're seeing up to these 15 kW or 20 horsepower ratings. PM motors really only shine once you get above that because they use rare earth magnet materials. They're a lot more expensive, more cost in them, difficult to service. They have very strong magnets in them that produces high back EMF, which is regenerative voltage, which can be a safety concern, etc. So not really utilized a whole lot in HVAC market for that reason. But I just presented here to just show you the different efficiency technologies that are out there. So, just in summary, the Center RM technology employs ferrite magnet materials, which are readily available and price stable and environmentally sustainable ceramics. They utilize maximum active materials to produce a really high efficiency, but as I'll show you, a flat efficiency map. So that efficiency is maintained not only at base speed and full load, but at partial speed and partial load points. High power factor and lower amp draw leads to a smaller drive converter. And it uses the standard building blocks of standard induction motors. So we can do a lot of configurability, high volume in standard production facilities, and have a stock product that's readily available and off the shelf. So let's take a look at your efficiency standards. There's NEMA standards here in the US, and then you have IEC that defines efficiency bands internationally. Here in NEMA, you have standard efficient, high efficient, premium efficient, and super premium, and they kind of align to IE 1, 2, 3, and 4 levels. There really is no NEMA standard yet for IE 5. It doesn't exist. Some people are using ultra premium, but NEMA hasn't actually defined that. Each band of efficiency is about 10% less losses in the motor. We already talked about losses. That's how you get into your different bands. You have to decrease motor losses to get higher efficiency. 60034-30-1 is the standard for IEC. It defines up to IE4 for direct across the line motors. There's a new technical standard, which is -2. It was implemented, it's not actually a standard, but just a technical standard at this point. It was implemented for motors like this, like the Center RM squared, that have to run on a drive, and they're not across the line. So it was created to have a standard out there that created a level playing field for that. So here's the actual defined efficiencies for the product. So when you look at the Center RM squared, it is these red lines, the blue lines up here, and this purple. The yellow dotted line here is 30-2. So that's the efficiency when you're running on a drive, and you can see we're well above that. So it's that's why we sometimes say IE5 plus, because in most cases we're not right at IE5, we're actually well above it. Now, why you see two different efficiencies here, again, that's the power density. So a 3 horsepower, we can put it in a standard 180 frame here, a little higher efficiency, more active material, or we can go down to a 140 NEMA frame with a little bit hit on efficiency. So it's just a matter of, do you want a smaller, lighter weight motor or the maximized efficiency? So, and again, that provides flexibility in your HVA system design. If you can take weight out of the system, it might allow you to do some more things creatively and innovatively with the HVAC system because you have a smaller, lighter weight motor. It's kind of an eye chart, I know, but just to line up IEC ratings with NEMA ratings, we're at a lower voltage on IEC, lower base speed, 1500 at 50 Hertz, a little bit more current draw, but we're still hitting the IE5 efficiencies here. And that's because we were already at IE5 plus. So they're a little lower efficiency than the NEMA. And that's just strictly because you're running it at a reduced voltage and higher current draw. Now, one of the things I want to highlight out here is I talked about lower current draw. So I wanted to show that. So here's a 1 horsepower, 2.3 amps at 230 volt, 3 amps for the induction design. So, there's a significant difference in the current draw, and depending on where you are here with your power converters, you may be able to get away with a smaller power converter. So, like for example, we're running a 5 horsepower on a 3 horsepower power converter because the power converter has 12 amps. So, it just depends on where you fall on this scale, but in a lot of cases, you can actually go down a size in the drive because of the lower current draws in the motor. So that's one of the things I wanted to highlight. So let's show some of the efficiency test data, and the key takeaways here too are, when I show the efficiency data, uh, most HVA systems never operate at full load and full speed. And that's because when uh, they're designed for the maximum operating and the peak load demand. And then in a lot of cases, they're designed for future capacity, and that's plus 10% to the capability of the HVAC system, which really results in when these are installed, they never really run at full load and full speed. They're more like 80% speed, and which is about 50% load, about 99% of the time. So you really to look at your design and say, well, what is my maximum wire to air efficiency at these reduced load and speed points? That's the critical part, not at the published efficiency IE5 standards. What's your motor doing to help you get the maximum efficiency at these partial load and partial speed points? I mean, there's other factors that come into it. Picking the right design, where the motor is located in the airstream, is it blocking the airflow, etc. If it's a package design, really the efficiency of each component isn't known. It's just the overall package efficiency. So it leads to maybe a little bit less innovation and design. You have to look at the drive converter. So is the drive controller efficient at those partial load and partial speed points? A standard uh, PWM inverter like the ABB ACH 580 is very efficient at partial load and partial speeds on these center RM squared motors. So, but in other cases they may not be, and at these reduced load points that contributes to lower overall efficiencies. So, also the drives let you go on standard on the center RM squared. We can run above base speed, and I'll show that efficiency operating region. So you get a wider peak efficiency below base speed and at partial load, but then you can also overspeed it. So if you need some additional headroom or your fan curve is just above where the base speed of the motor, we can just overspeed it and increase the overall capability of the system. So again, this is the affinity laws. Most everyone knows this. You run at slower speeds. It's a cube rule of load, so your power drops, so 80% speed, 51% load. So that's why you really have to look at these systems aren't really running at full load and full speed. So what's your actual wire air efficiency is at these reduced points? And so this is actual lab testing, comparing the different technologies. And what we're trying to produce with the center RM squared motor is a motor that you, as a designer of the HVAC system, becomes a constant. So you can now say, I'm guaranteed to hold a relatively flat efficiency profile all the way at base speed and above base speed, down here in these partial load points, down into where I'm typically operating at 80% speed and 51% load points. And I'm not dropping hardly any efficiency, versus the other technologies tend to drop off more rapidly. So that way you get a constant known baseline, and you can apply that motor to the best pump or fan curve for the system with the best efficiency. And there can be a wide efficiency difference because there's just a lot of variables. And so like if you look at a fan design, there's a lot of variables associated with picking the right fan. You got the speed of the fan, the diameter, the wheel width, number of blades. So, when you get into the fan selection programs, there's a lot of variables there, and you can get really wide differences at on these curves to the efficiency of the fan, and it's the primary contributor to efficiency losses at partial load and speed. So if I can give you a motor that widens your selection of fan designs, it gives you more ability to pick the right design that's going to maximize the wired air efficiency for whatever system requirements there are. So that's the intent here for this product. We think we can allow a lot more innovation and flexibility for HVAC designs. And I kind of already touched on what we said here. In our testing, the design region for maximum efficiency on traditional EC designs is a little bit more limiting. It requires that the fan design really be more fitted to the best motor operating region. And we're saying, no, instead, we're going to fit our motor to the best fan efficiency operating region. You can see some of the results here. These are just on standard fan curves. Full disclosure, this green line's an EC motor, so you can get really good efficiency if it just happens to match up to the right system. And then these are some other EC fans. And then this gray line is a center RM squared motor on a OEM fan curve, and these middle lines. So by doing this design, you can pick out different fan curves, different pump curves, and really just pick the optimal one for the system. And this is how we're doing it. We're just giving a very wide, what we call efficiency island. So stay on that island for your design region. And so you can run it above base speed if your fan curve's out here, and you've got this nice flat 94% efficiency region above base speed to operate in. And as you slow it down, you can get down here into half speed before the efficiency hardly drops off at all. You're still at 92%. So that gives you a lot of flexibility. I can shift different fan curves in here, whatever gives me the peak wired air efficiency for my system. And anywhere you're on this efficiency island, we've got a known quantity with this motor efficiency. And by the way, if this efficiency island at 1800 RPM doesn't make the fan curve, well, fine. We've got 900 base speed, 1200, 18, 3600 RPM base speed motors. So I can take this efficiency island and just shift it all over the place, wherever it needs to be for the best HVAC wired air efficiency design. So that's the message here on maximizing wired air efficiency. Again, I'll reiterate on this. It uses standard components. So if you're replacing an induction motor, this is a drop-in replacement for that. It uses well-known power converters like the ABB ACH 580, which has firmware directly to support this motor design. So they're standard discrete components. They're easy to integrate and they're readily available. So these are all stock components that we just put together and provide as a system. It allows drop-in replacements, but also really, ease of service. So you're not like taking out that whole fan assembly, motor, and drive. You can service individual components. And it gives, the superior performance that I already talked about. The standalone ACH 580 also gives you additional capability. Standard permanent magnet motors and electrically commutated motors put out harmonics in non-traditional points, so they're not really easy to mitigate any harmonics. And with this, you can use a standard power converter like the ACH 580. It has a 5% DC link choke with built-in harmonic mitigation. If you really want to step up and get rid of the harmonics, there's the ultra low harmonic capability. So if harmonics are a concern, we think this is a better solution as well. Because it is on a drive, we also put a standard ground brush in these to get rid of bearing currents and common mode voltage. We can do ceramic bearings and things like that as well. I think a ground brush is better because it takes any shaft currents and shunts it to ground. Ceramic bearings, they're great for protecting the motor, but you have to ask the question. It doesn't take that common mode voltage and shaft current to ground. It went somewhere, it didn't go to ground. So, where did it go and is it damaging any of the driven equipment? So I tend to I tend to prefer a shaft ground brush for that reason. It's a known quantity, takes that and takes it right to ground and gets it out of the system. So just as a summary, this is the initial product offering. We will be actually launching, I have a meeting this morning to finalize the ratings design and CE approval. So we will have IEC stock versions of this probably in the next month. These are the ratings that it's available as a center arm squared. We call it the EC titanium. We actually use that name. It's more of a marketing term because, again, this is not an electrically commutated motor. It's a second generation center RM motor. But it's really kind of come known, at least here in the US, a lot of the specs will actually call out and ask for EC motors. So we use that in the name. It's more for marketing than anything because it's just kind of known for high efficiency, and some specs actually call out EC motors. So again, just to summarize, IE5 efficiency minimizes environmental impact, less losses, less energy, but also sustainable non-rare earth ferrite materials. There are integrated drives and motors. I already talked about the benefit of the standalone drives, but you can get it with an integrated drive if you just want something that's a drop-in, plug-and-play, say panel space. It's extremely low starting current because of the ferrites and low noise. So it adds, it's a very quiet running product, comparable or lower than induction motors. So it'll be quiet in the system, and then power density for reduced size and weight in the system. And this is actually from a voice of a customer feedback. And, they just reiterated some of the points I was making, and we talked through this. And they stated that as an OEM, that total system efficiency is the primary focus of their improvement. Again, they mentioned that agencies like the Department of Energy are trying to pass regulations on wire-to-air efficiency. They've been pushing back because they're saying there's just so much variability in how the fan is designed, and if they were to regulate the wire-to-air efficiency, that would hurt innovation. So they want them to not do that, so that they can innovate and provide the highest efficiency product into the market. And based on their analysis, efficiency is only part of the story. The center arm squared motor gives them a lot of flexibility, and it allows them to innovate and pick out the best fan design that's going to maximize the total wire-to-air efficiency. And so they said that's why they like this product, and they selected it because it allows them to innovate and be more flexible in their HVAC designs. So that's what I had for my brief summary today, just as an introduction to the technology, why we think it's different, and what it adds as far as system value. And we can open it up for any questions you might have. Which also, I think they just type in chat, right?
Yes. So let's give a couple of minutes time to come up with interesting questions if some might have. But meanwhile, thank you very much, Mark, for this great presentation, and
you're welcome.
Really great to see that we and the customers have such unique opportunity for energy savings with this motor technology, and not only for energy savings, but much more. And I guess if there is no questions right now, we of course always can turn to you. Yeah, there is a comment and appraisals from Katya. Great presentation. Thank you. Thank you, Mark, once again. And yes, as mentioned, if any further questions, don't hesitate to contact Mark. There is one question actually. What is the abbreviation SYNRM2?
The abbreviation, it just stands for synchronous reluctance with ferrite assisted technology. So it's just second generation of the synchronous reluctance rotor motor from ABB.
Good. That's an easy one. Thank you.
Welcome.
So far, no more. Then the rest is easy and clear.
Well, thank you everyone for joining. Please feel free to ask follow-up questions. I'll be happy to respond.